Welcome back to the deep dive.
Good to be here.
So today we're tackling a topic that's constantly reshaping our planet, literally right under our feet sometimes.
Rivers.
Exactly, running water. We're going to explore how rivers start, how they cart out landscapes, and, the whole journey they take.
Yeah, and our deep dive today draws heavily on some really solid geographical source material.
Yeah.
Specifically, a text that goes into great detail about the landforms created by running water.
Right. So the mission basically is to trace a river's life from like a tiny trickle high up somewhere all the way down to the sea.
And understand the immense power involved, the incredible features they create over time. It's fascinating.
It really is. And I think once you start understanding these processes, you genuinely look at landscapes differently. You start spotting things.
Absolutely. You see
Yeah.
a valley or a bend in a river and you think, I know what's going on there.
All right, so let's jump in. Where does it all begin? The birth of a river system.
It all starts with precipitation,
Mhm.
rain mostly.
Falling on the ground. Simple enough.
Well, yeah, but then what happens? Some of that water soaks into the ground, becomes groundwater. Some evaporates straight back into the atmosphere.
Okay.
And the rest, the water that flows over the surface, that's what we call runoff. And that's the crucial part for rivers.
That runoff, and it doesn't just stay as a sheet, does it? It starts to gather.
Exactly. Gravity pulls it downhill, and it naturally collects in tiny depressions, forming little channels. These grow into rivulets.
Rivulets, okay.
Then those join up to form brooks, which feed into streams, and eventually, as they gather more and more water, they become rivers.
And right from the get-go, this water is doing work on the land.
Oh, absolutely. This running water immediately becomes a really powerful agent of what geologists call denudation.
Denudation, okay, let's pin that down. It means wearing away the Earth's surface, right?
That's the core idea, yes. It's the overall process of lowering the land surface through erosion and weathering. And the source material really emphasizes that running water is arguably the most important single agent of denudation globally.
More important than, say, glaciers or wind.
On a global scale, yes. While glaciers are incredibly powerful where they exist and wind shapes deserts, running water is active almost everywhere there's enough rain and a slope. It's constantly loosening, dissolving, and crucially, removing earth material.
Okay, so removing is key. That brings up the difference between weathering and erosion.
Exactly. Weathering is the breakdown of rocks in place. Frost shattering a rock or acid rain dissolving it. It doesn't move.
Right.
Erosion, on the other hand, is both the breaking down and the transportation of that material. So rain splash, wind, ice, waves, and running water, they all erode because they move the debris.
And running water is just particularly good at the moving part.
It's incredibly efficient and widespread. Think about it. Rain falls almost everywhere. Water flows downhill almost everywhere. So globally, it's just relentlessly active, carrying vast amounts of material away.
That really puts its importance into perspective. Okay, so we have runoff forming streams. Where does a river officially begin? The source.
The source is typically where the flow becomes more defined. It could be a spring bubbling up, or the outlet of a lake, or even a marshy, saturated area in usually an upland region.
Uplands make sense. You need that elevation for gravity to do its work.
Precisely. The areas with the heaviest rainfall and the steepest slopes are where you get the most concentrated runoff and the highest energy right from the start.
And the whole area that collects water for a particular river system, that's the catchment area.
Yes, the catchment area, or sometimes called the drainage basin. Think of it like a big funnel in the landscape. All the rain falling within that basin's boundary eventually finds its way into that river.
And those boundaries are called watersheds.
Exactly. Watersheds are the high points, the ridges, that divide one catchment area from the next. Rain falling on one side of the ridge flows into one river system, and rain on the other side flows into another.
Makes sense. So the very first streams that just flow straight down the slope following the land's initial gradient, what are they called?
Those are called consequent streams. They're the first ones established just following the consequence of the slope.
Okay, and then other streams join them.
Right, tributaries.
Hmm.
These are subsequent streams that develop later and join the main consequent stream. Where and how they join the angle, for instance, can often be influenced by the underlying geology. Things like rock type, hardness, faults.
Ah, so the rocks underneath start controlling the river's path.
They definitely can, which leads us directly into the idea of drainage patterns. The overall shape the river network makes on the landscape isn't random.
It tells a story about the geology.
Absolutely. The pattern is a direct reflection of the underlying structure and walk resistance. The source highlights two main types. First, dendritic drainage.
Dendritic, like dendrite meaning tree-like.
Exactly. It looks just like the branching pattern of a tree or its roots. You have the main river as the trunk, and tributaries joining at usually acute angles like branches.
And why does it form that tree shapes?
It typically develops where the underlying rock is homogeneous, meaning it's pretty much the same everywhere, offering uniform resistance to erosion, or it can form on flat-lying sedimentary rocks. Because there's no geological structure guiding the water in specific directions, the streams just spread out naturally, following the slope, like roots seeking water.
So a tree pattern means the rock underneath isn't really bossing the rivers around. What's the other main type? Trellis.
Trellis drainage, yes. This looks much more organized, almost like a garden trellis, with a rectangular or grid-like pattern.
Okay, why rectangular?
This pattern forms where you have alternating bands of hard and soft rock that have been folded or tilted. The main, longer streams tend to carve their valleys along the lines of the weaker, softer rock because it erodes more easily. Then, shorter tributaries flow down the steeper slopes of the harder rock ridges and join the main streams at or near right angles. They often follow faults or joints across the harder rock, so the whole network looks angular, reflecting that underlying geological control.
That's fascinating. So you can almost read the hidden geology just by looking at the river map. Dendritic means uniform rock. Trellis means alternating hard and soft bands.
It's a fantastic visual clue to what's going on beneath the surface.
The source also briefly mentions the broader picture of erosion in humid areas. It's not just the river channel itself.
No, that's a good point. While the river channel is where the most focused erosion happens, the overall shaping of the landscape in humid regions also involves, the direct impact of raindrops splashing soil and, importantly, mass movement.
Mass movement? Like landslides?
Exactly. It's the downslope movement of soil and weathered rock material, primarily driven by gravity, but heavily influenced and often triggered by water. Water adds weight, it lubricates layers, and it can increase pore pressure, weakening the slope.
So gravity pulls, but water helps it slip.
Precisely. The source mentions soil creep, which is that super slow, almost invisible downhill ooze of soil. You might see tilted fences or trees on a slope as evidence, but it also includes more dramatic events like landslides, especially common in steep mountainous areas, particularly after heavy rain saturates the ground. These can happen suddenly and be incredibly destructive.
Blocking roads, railways, even burying villages, as the source notes.
Yes. So the denudation process includes both the river carving its channel and the material moving down the valley sides towards the river, often aided by water saturation. It's all connected.
A whole system working together to wear down the land. Okay, so the river is carving and material is moving towards it. The river then has to transport all this stuff, right?
Absolutely. Erosion is only half the story. Transportation is the other critical function. All the material picked up by the river, from dissolved minerals to giant boulders, is called the river's load.
The river load, and it's carried in different ways.
Yes. The source breaks it down into three main types of load, based on how the material is carried.
Okay, what are they?
First, you have the dissolved load. This is material that's actually chemically dissolved in the water itself. Think of salts or calcium carbonate from limestone. You can't see it, it's in solution.
Invisible transport, got it.
Second is the suspended load. This is the fine stuff. Clay, silt, maybe very fine sand. These particles are light enough that the turbulence of the flowing water keeps them mixed up within the water column, suspended, not settling on the bed.
Is this what makes rivers look muddy or brown?
Exactly. Especially after rain, when lots of fine sediment gets washed in, that cloudy look is the suspended load.
Okay. And the third type?
The third is the traction load. This is the heavier, coarser material. Pebbles, stones, rocks, even boulders. They're too heavy to be suspended, so they move along the riverbed.
How do they move? Just pushed along?
They're rolled, slid, or bounced along the bottom by the force of the water. This process is called traction, or saltation for the bounce of motion.
You mentioned hearing a grinding sound in rivers earlier. Is that the traction load?
That's precisely it. It's the sound of these larger rocks grinding against the riverbed and colliding with each other. It's direct evidence of erosion and transportation happening.
The scale of this load must be enormous.
It's staggering. The source gives figures suggesting hundreds, even thousands of tons of material are removed per square mile of land surface each year by rivers. And it mentions the Mississippi River carrying millions of tons of sediment to the Gulf of Mexico every day.
Millions of tons. Daily. Just from one river. Wow.
It really hammers home why running water is considered such a dominant force. And all this transport is driven by the river's erosional processes, which the source breaks down into four main types.
4 ways the river actually wears away the land and picks up its load.
Yes, and these often happen simultaneously. The first is corrasion, which is also called abrasion.
Corrasion or abrasion? That sounds like scraping or grinding.
That's exactly what it is. It's mechanical grinding. The river uses the rocks. It's already carrying the traction load as tools. These rocks scrape against the riverbed and banks, wearing them away like sandpaper.
So the river uses its own load to erode more.
Precisely. It's a very effective process. And the source distinguishes between vertical corrasion, which deepens the channel by grinding the bed downwards,
Okay.
and lateral corrasion, which widens the channel by grinding away at the banks sideways.
Downward and sideways grinding.
Got it. What's next? Next is corrosion. Notice the O, also called solution. This one is chemical, not physical.
Ah, different process.
Totally different. Corrosion is when the river water itself dissolves certain types of rock it flows over. Limestone is the classic example, being rich in calcium carbonate, which dissolves in slightly acidic water. This dissolved material becomes part of the dissolved load.
So corrasion grinds, corrosion dissolves. Okay, third.
Third is hydraulic action. This is the physical force of the moving water itself.
Just the water. No rocks involved.
Primarily just the water's force. Think of turbulent water being forced into cracks in the banks or bed. The pressure can wedge these cracks open, dislodging pieces of rock. Also, the sheer force of water hitting the banks can sweep away loose material or undermine softer rock layers.
The raw power of the flow. Makes sense. And the fourth one.
The fourth process is attrition. This one is interesting because it doesn't directly erode the river channel itself.
What does it do then?
Attrition is the process where the particles of the river's load collide with each other as they're being transported.
Ah, the rocks bashing into each other.
Exactly.
Yeah.
Pebbles knock against boulders, stones grind against each other. This action breaks down the larger pieces into smaller ones, and importantly, it wears away their sharp edges and corners.
Is that why river pebbles are usually smooth and rounded?
That's precisely why. Attrition smooths them down over time. And the finer material produced by this process gets added to the suspended or dissolved load and carried further downstream.
Okay, let's recap the four. Corrasion, grinding with load. Corrosion, chemical dissolving. Hydraulic action, water force. And attrition, load particles hitting each other.
Perfect. And these processes work together, but their relative importance changes depending on where the river is in its journey from the mountains to the sea.
Which leads us nicely into the different stages or courses of a river. The source talks about the upper, middle, and lower courses.
Exactly. It's like following the river through its life stages, from youth to old age, though geologists prefer courses. Let's start at the beginning, the upper course.
High up in the mountains, near the source. What are the key characteristics here?
Steep gradient is the main one. The river is flowing rapidly downhill. Velocity is usually high because of the slope, although the actual volume of water might be relatively small compared to downstream, as it hasn't collected many tributaries yet.
And the dominant process here is that downward cutting.
Yes, vertical corrasion absolutely dominates. The river's energy is focused on cutting down into the land. Lateral or sideways erosion is much less significant at this stage.
And this intense downward cutting creates a specific valley shape.
The classic V-shaped valley. Because the river is cutting down so aggressively and the valley sides are simultaneously being weathered and shedding material downwards via mass movement, you get these steep sides meeting at a narrow floor where the river is actively carving. The V-shape forms because downward erosion outpaces sideways widening.
Makes sense. What if the rock is really tough, but the river keeps cutting down?
Then you get even more dramatic features.
Yeah.
Gorges and canyons. These are extremely deep, narrow valleys with very steep, sometimes vertical rock walls. They form where rapid vertical corrasion occurs in resistant rock over long periods.
Like the Grand Canyon.
Exactly. The source mentions the Indus Gorge, the Grand Canyon, Colorado Canyon, and Bryce Canyon as prime examples. They are monuments to the persistent power of river erosion over geological time.
It's mind-boggling. Okay, what else happens in the steep upper course? Waterfalls?
Definitely. Rapids, cataracts, and waterfalls are common features. Rapids occur where the gradient suddenly steepens locally, or there are obstructions like bands of hard rock crossing the channel, making the flow fast and turbulent.
And waterfalls are the really big drops.
Yes. Waterfalls typically form where a layer of hard, resistant rock lies on top of the softer, less resistant layer. The river erodes the softer rock underneath more quickly through hydraulic action and abrasion from swirling pebbles.
Undercutting the hard layer.
Exactly. Eventually, the overhanging hard layer becomes unsupported and collapses. This process causes the waterfall to gradually retreat upstream over time, leaving a gorge behind it.
And that deep pool at the bottom of a waterfall.
That's the plunge pool. It's excavated by the sheer force of the falling water hitting the bottom and also by the intense grinding action of rocks turned around in the turbulent water at the base.
The source mentions some huge examples.
Yeah, Niagara Falls, Kaitur Falls in Guyana, incredibly high at 825 feet, and Victoria Falls in Africa. They really showcase the erosive power concentrated at these points.
Amazing. There's one more upper course feature mentioned that sounds really dramatic. River capture.
River capture, or river piracy. It sounds exciting, and it is, geologically speaking. It's when one river, usually a more energetic one, with faster headward erosion.
Headward erosion, meaning eroding backwards towards its source.
Yes, exactly. A river eroding backwards, often because it has a steeper gradient or more water volume, can cut through the watershed divide, separating it from a neighboring river.
And steal its water.
Essentially, yes. It intercepts the upper course of the other, usually less energetic, river, and diverts that water into its own channel. The capturing river gets bigger, and the beheaded river loses its headwaters.
What happens to the captured river's lower part?
It's left with much less water, sometimes becoming what's called a misfit stream, looking way too small for the large valley it flows through. And the abandoned valley section where the capture happened might be left high and dry as a wind gap.
Wow, rivers actually battling it out over landscapes.
It's a dynamic process of drainage networks evolving over long time scales.
Okay, so that's the upper course. Steep, fast, cutting down, creating V-valleys, gorges, waterfalls, and even stealing water sometimes. What happens when the river leaves the mountains, the middle course?
Right. As the river flows onto gentler slopes, it enters the middle course. The gradient lessens, but there's still significant energy.
Less steep means less downward cutting.
Yes, vertical corrosion slows down. It still happens, deepening the valley gradually, but is no longer the dominant force. Now, the river starts to expend more energy, eroding sideways. Lateral corrosion becomes much more important.
And it usually has more water now too, right?
Definitely. It's been joined by more tributaries, so the volume and discharge increase significantly.
So more water, more sideways erosion. The valley starts to change shape.
It does. The valley floor begins to widen, moving away from that tight V shape. The slopes become gentler. In the transition zone, you often see interlocking spurs.
Interlocking spurs, what are those?
As the river starts to meander slightly around ridges of more resistant rock that jut into the valley, these ridges, when viewed from downstream, appear to overlap or interlock. It shows the river beginning to swing side to side instead of just plowing straight ahead.
And that swinging side to side leads to the classic river bends, meanders.
Exactly. Meanders are those sweeping loops and curves that become really characteristic of the middle and lower courses. They start from slight irregularities in the channel, and then a specific process makes them grow.
What's that process? It's not just random winding.
No, it's driven by differences in water speed within the bend. The water flows fastest on the outer bank of a meander bend.
Why faster on the outside?
Partly due to inertia or centrifugal force as the water swings around the curve. This faster flow on the outside has more energy, so it erodes the outer bank through corrosion and hydraulic action. This creates a steep bank, often undercut, called a river cliff.
Okay, erosion on the outside bend. What about the inside?
On the inside of the bend, the water flows more slowly. Because it's slower, it has less energy and starts to deposit some of its sediment load. This builds up a gently sloping area of sand or gravel called a slip-off slope or point bar.
So, erode the outside, deposit on the inside.
Precisely. And that's the engine driving meander growth and migration. The erosion on the outside makes the bend wider, while the deposition on the inside builds it inwards. This process causes the meander loops to become more exaggerated and to slowly shift their position across the valley floor over time, often migrating downstream as well.
They're actually moving features.
Absolutely. They're constantly reworking the floodplain, widening the valley. So the middle course is this transition. Less vertical cutting, more lateral cutting, valley widening, and the development of these migrating meanders. Deposition starts to become noticeable, especially on those inner bends.
The river's sort of maturing.
That's a good way to think of it. It's balancing erosion and transport, starting to shape a wider domain for itself.
Okay, which brings us to the final stage. The lower course, sometimes called the plain course or old age stage.
Right. This is where the river flows across very flat land, often near sea level or the large lake it flows into. The gradient is extremely gentle.
Almost flat. So the water must be moving pretty slowly.
The velocity is much lower, yes. Even though the volume of water is usually at its greatest here, having collected all its tributaries, the lack of slope means there's very little energy for erosion.
So what's the main job of the river now?
Deposition. It becomes the dominant process. The river simply doesn't have the energy to carry all the sediment load it picked up upstream. Lateral corrasion pretty much ceases. It's all about dropping the load.
It's like a conveyor belt reaching its endpoint.
Exactly. And this widespread deposition creates a whole new suite of landforms. The valley becomes extremely wide and flat. This is the alluvial plain, built up layer by layer from river-deposited sediment, alluvial.
Oh, alluvial plain. Made of river deposits. Okay, what about the river channel itself? Does it stay as one channel?
Not always. If the river is carrying a huge amount of sediment, especially coarser stuff, and the gradient is very low, it can start dropping sediment right in its own channel, forming sand and gravel bars.
Choking itself up.
Kind of, yeah. This can force the flow to split into multiple smaller channels that weave around these bars. This is called a braided stream. You see this often in front of melting glaciers where there's tons of sediment.
Braided, like strands woven together. Interesting. The most famous feature here, though, is probably the floodplain.
Definitely. Floodplains are those wide, flat areas bordering the river channel. They're built by floods.
How so?
When the river discharge gets too high for the channel, it overflows its banks. As the water spreads out over the flat plain, its velocity drops dramatically.
Losing energy instantly.
Right. And as it loses energy, it drops the fine sediment it was carrying, the silt and clay from the suspended load. Over countless floods, these layers of fine sediment build up, creating the characteristically flat and very fertile floodplain.
Ah, that's why they're so good for farming. The river brings the fertilizer.
Exactly. It's natural fertilization and irrigation. The source mentions the great agricultural plains of the Indus, Ganges, and Freya rivers as examples built this way.
Of course, flooding itself is also the big risk there.
Absolutely. It's a double-edged sword. Another classic lower course feature, linked back to meanders, is the Oxbow Lake.
Right, those crescent-shaped lakes you see abandoned near rivers. How do they form again?
As a meander loop becomes more and more exaggerated, the neck of land between the start and end of the loop gets progressively narrower.
The river almost loops back on itself.
Exactly. Then, often during a flood, when the river has extra energy and volume, it takes the shorter, easier path and cuts straight across that narrow neck.
Takes a shortcut.
Precisely. Once the main flow is going through the new, shorter channel, sediment gets deposited at the entrances to the old meander loop, eventually sealing it off completely. What's left is the abandoned loop, filled with water, the crescent-shaped Oxbow Lake.
Which eventually fills in.
Yeah, over time they fill with sediment and vegetation, becoming marshes, and eventually just scars on the floodplain.
Okay. And then, the very end of the line, the river meets the sea or a big lake. This is where we find deltas.
Deltas, yes. These are typically fan-shaped or triangular accumulations of sediment deposited right at the river's mouth.
Why do they form there?
Because when the river flows into the still water of the ocean or lake, its velocity drops almost to zero very quickly. It loses all its remaining energy to carry sediment, so the vast majority of its load gets dumped right there at the mouth. Over time, this pile of sediment builds outwards, creating new land, the delta.
But not all rivers form big deltas, right? What
Right.
conditions are needed?
That's key. The source lists several factors. Firstly, the river needs to be carrying a large sediment load. If it's filtered by lakes upstream or trapped by dams like the Nile now, the delta won't grow much.
Okay, lots of mud and sand needed.
Secondly, the coastal area, or lakeshore, needs to be relatively shallow, allowing sediment to accumulate. If it drops off steeply, the sediment just disappears into deep water.
Makes sense.
Thirdly, the mouth area should be fairly sheltered from strong waves, currents, and tides. If the sea is very energetic, it will just wash away the sediment as fast as the river delivers it.
So calm seas help build deltas.
Generally, yes. And
Yeah.
fourthly, as mentioned, no large lakes upstream acting as sediment traps.
So it's a balance between sediment supply and removal by the sea. And deltas come in different shapes.
They do, reflecting the balance between river deposition and marine processes. The source describes a few main types. There's the bird's foot delta, like the Mississippi,
Why bird's foot?
because the river splits into multiple channels called distributaries, and deposition occurs mainly along these channels as they extend outwards into the sea, looking like the spreading toes of a bird's foot.
Okay, finger-like projections.
And there's the arcuate delta, which is
Yeah.
the more classic fan or triangular shape with a curved seaward edge. Examples are the Nile, Ganges, and Mekong. This suggests a more balanced distribution of sediment, perhaps smoothed by some wave action.
A rounded fan. Got it.
Estuarine deltas form within estuaries, those funnel-shaped, often drowned river mouths. Sediment gets deposited along the sides of the estuary rather than building far out to sea. The Ebro in Spain is an example.
So filling in the estuary.
Kind of, yes. And finally, cuspate deltas are pointed or tooth-shaped, often formed where strong wave action pushes sediment back towards the coast on either side of the river mouth.
Different shapes tell different stories about the river and the sea interacting.
Absolutely. It's the final signature of the river's journey.
So that covers the three main stages, but the source mentions something called river rejuvenation, like the river gets young again.
In a way, yes. Rejuvenation means the river regains erosive power, particularly downward cutting, often in its middle or lower course where it had previously slowed down.
What causes that? How does an old river get young again?
It's usually caused by a change in the relative level between the land and the sea, what the source calls negative movement. This could be tectonic uplift of the landmass the river is flowing over.
The land goes up.
Or the sea level itself could fall, perhaps significantly during an ice age when lots of water is locked up in ice sheets.
Sea level drops.
Either way, the effect is the same. It increases the river's gradient, especially in its lower reaches. Suddenly, that gentle slope becomes steeper relative to the base level the river's flowing towards.
So the river gets a steeper path to the sea, giving it more energy.
Exactly. It gets a new burst of erosive energy and starts cutting downwards again, incising into its former floodplain.
And this creates some distinctive features that look maybe out of place.
It certainly does. One key indicator is a nick point.
Nick point.
It's a sharp break, like a step, in the river's long profile, the graph of its gradient from source to mouth. It marks the point where the river's new, steeper, rejuvenated profile meets the older, gentler profile. Often you see rapids or even a waterfall at the nick point, and this nick point gradually migrates upstream as the wave of renewed erosion works its way back up the river system.
Like a little waterfall moving backwards up the river over time.
That's the idea. You also get features like rejuvenated valleys or valleys within valleys. The river carves a new, deeper, often steeper-sided inner valley into the floor of its older, wider, flatter valley that existed before rejuvenation.
You can see the old valley floor as terraces high above the current river.
Exactly. Those are often remnants of the old floodplain. But perhaps the most spectacular evidence is incised meanders.
Incised meanders, so meanders cut deep into rock.
Precisely. Imagine those wide, sweeping meanders the river developed on its flat floodplain during its mature or old stage. Then the land uplifts, or sea level drops. The river starts cutting down vigorously, but it's already stuck in its winding path.
So it just cuts straight down following the bends.
Yes, it carves those existing meander patterns deep into the bedrock, creating deep, steep-sided winding gorges that follow the meander shapes. They look like upper course gorges in terms of depth, but have the sinuous pattern of lower course meanders.
Where can you see those?
The source gives great examples. The River Wear cutting through Durham in England, looping around the Cathedral Peninsula in a deep gorge, and the Wye Valley on the border of England and Wales. They are dramatic proof of rejuvenation. The meanders formed low down, then uplift forced the river to entrench them.
That's amazing. It's like geological history written right into the shape of the river valley.
It really is. It shows rivers are constantly adjusting to these larger-scale geological changes.
So rivers shape the land, but they are also profoundly shaped by geology and climate changes over time. And of course, they are hugely important to humans. The source finishes by looking at the human aspects.
Yes, both the benefits and the challenges rivers present to us.
The benefits seem huge. Navigation, for starters.
Absolutely fundamental throughout history.
Yeah.
Rivers provide natural highways deep into continents. The source lists so many major examples: the Yanks, Amazon, Mississippi, Rhine, Danube, Congo, Nile, all vital arteries for transport, trade, and settlement. That's why so many major cities are located on rivers.
And the obvious one, water supply.
Critical. Fresh water for drinking, for industry, and crucially for agriculture through irrigation. Think of those huge irrigation systems fed by rivers like the Indus and Ganges, supporting vast populations by allowing farming in drier regions.
And the land itself, those fertile floodplains and deltas we discussed.
Hugely valuable agricultural land. The natural deposition of silt makes them incredibly productive. The Nile Delta, the Ganges Delta, cradles of civilization, partly because of that river-supplied fertility.
Plus energy from rivers.
Hydroelectric power, yes. especially in the steeper upper and middle courses where dams can be built in gorges to harness the water's energy for electricity generation, a major renewable energy source.
So, transport, water, fertile land, power. Rivers provide so much, but they also pose challenges.
Big challenges.
Yep.
Flooding is the most obvious and often devastating one. The very process that creates fertile floodplains also threatens lives and property.
And rivers don't always stay put, do they?
No, especially in their lower courses. They can naturally shift their channels over time, a process called avulsion. This can undermine infrastructure, change land boundaries, and disrupt settlements.
And all that sediment they carry can cause problems too. Siltation.
Yes, the deposition that builds deltas can also choke river mouths and harbors, hindering navigation. Ports on major rivers often require constant, expensive dredging to keep channels open.
And our attempts to control rivers, dams, levees, they have consequences too.
They certainly do. Dams trap sediment, which can starve downstream areas of fertile silt and cause deltas to shrink or erode. Levees constrict rivers, which can prevent beneficial flooding on the floodplain, but might increase flood heights within the levees and cause worse disasters if they fail. The source mentions the Huanghe Yellow River in China, historically called China's Sorrow because of catastrophic floods, as an example of the immense challenges and complex consequences of trying to manage such a powerful river system.
It really highlights that complex relationship humans have with rivers utterly dependent on them, but also constantly battling their power.
They are truly dynamic systems, intertwined with geology, climate, and human society.
Well, this has been a fascinating journey following the river from source to sea. We've seen the incredible power of vertical erosion carving gorges, the sideways shift creating meanders and wide valleys, and the patient work of deposition building vast plains and deltas.
And how the river's story can be reset by geological forces, leading to features like incised meanders that tell tales of past landscapes. Rivers are truly sculptors of the Earth's surface.
We started off by noting the source calls running water the most important single agent of denudation. Thinking about everything we've discussed, the scale of the Grand Canyon, the vastness of the Mississippi Delta, the constant transport of millions of tons of sediment, the reshaping of entire landscapes through capture and rejuvenation, what does that tell us about how we should perceive geological time and the constant ongoing change happening on our planet's surface?
I think it forces us to see the Earth not as static, but as incredibly dynamic, even if the changes seem slow on a human timescale. Rivers demonstrate that seemingly gentle forces, applied persistently over vast stretches of time, can produce immense transformations. They carve mountains down, build new land out into the sea. They are a constant visible reminder that the geological processes shaping our world are powerful, relentless, and happening right now. They really embody geological time in action.